eigenvalues and eigenvectors now are taking the idea of a determinant. I mean, not the idea of a determinant, but using the determinant to find these values, and it's a whole step-by-step process that I'll go over. But we basically have a matrix. Let's say it could be like a 2 by 2 acting on a vector, and this is equal to a constant times a vector. And this is just an example. These aren't actual terms. I guess it should be more like x1, x2, something like that. I just put 2's down. I don't know why exactly. But we have this linear transformation, this matrix, acting on this vector. And the result is that we have this vector that is just scaled by some constant. This is essentially what the eigenvalue problem is. So let's say we have a matrix 1, 2, 3, 4. To find the eigenvalues, what we're going to do is let's say we define this as A. We say A minus lambda I equals 0. Well, sorry, that's not the entire thing. A minus lambda I times the x vector is equal to the 0 vector. So the first thing we do is we subtract, I'll just write it like this, 1, 2, 3, 4 minus lambda I. So this is going to be lambda times 1, 0, 0, lambda times 1. And then that's going to be acting on a vector, and then that's going to be equal to the 0 vector. But so we can combine the two matrices into one, and also keep in mind that we want non-trivial solutions. So we want solutions when the x vector does not equal the 0 vector. So the only way that that's going to be happening is when the determinant of this matrix is some value. So we take the determinant, so we have 1 minus lambda 0, well, not 0, 2, 3, and then 4 minus lambda. These ones kind of should be erased because it's just lambda. So we do that. Now we take the determinant of this, 1 minus lambda times 4 minus lambda minus 3 times 2. Oh look, a quadratic. A wild quadratic appears. Whatever can we do? For this one, we're going to have to use a quadratic equation. So minus 5 plus or minus the square root of 5 squared minus 4 times 1 times negative 2 all over 2 times 1. And after crunching all the numbers, we get 5 plus or minus the square root of 33 over 2. And this is not a very fun example to find the eigenvectors on, because you have to plug this back into this matrix and then find the values. But I have another nice example. So we have 3, 2, 4, 1. We plug this into our eigenvalue equation. We get 3 minus lambda, 2, 4, 1 minus lambda. Take the determinant and set it equal to 0. So we have 3 minus 3 lambda minus lambda plus lambda squared, or lambda squared minus 4 lambda minus 5 is equal to 0. Here we can easily factor what multiplies the negative 5 and adds the negative 4. So that's going to be plus 1 and minus 5, because we get lambda squared minus 5 lambda plus lambda, so that would be minus 4 lambda, then minus 5. Now remember, that's equal to 0, so we have lambda is equal to negative 1, or lambda is equal to 5. Because we solve these individually, this is what we get. So 2 eigenvalues as we are expecting. So now we plug this back into the original matrix. Well, not the original matrix, but the eigenvalue matrix to get the eigenvectors. So three minus 5, 2, 4, 1 minus 5, and that is equal to negative 2, 2, 4, minus 3. Oh, minus 4, sorry. We then say that this matrix is acting or multiplying on a vector that I'm trying to draw. So it'll look something like this. So we can actually row reduce our matrix, and this will give us 1, negative 1, 0, 0. Now, moving on to lambda is equal to negative 1, we have 3 minus 1, 2, 4, 1 minus 1. This comes out to 4, 2, 4, 2. So we have 4, 4, 2, 2 acting on, and that's equal to 0, 0. And we could just row reduce. That would be 1, 1 half, 0, 0, x1, x2. And then just write out the system. x1 plus x2 over 2 is equal to 0, because this bottom row doesn't really give us anything. Or x1 is equal to negative x2 over 2. So we can say, and I kind of glossed over the last one because they were both equal. It was really easy to say, well, just 1, 1 because they're both equal. Here it's a little different. We could say x1 is equal to 1, so that x2 is equal to, have that backwards. So we say x2 is equal to 1. x2 is equal to 1. Then x1 is equal to minus 1 over half, minus 1 over 2. So that our second eigenvector, v2, is then equal to minus 1/2, 1. So to summarize the entire process, we have this matrix 3, 2, 4, 1, which we found our eigenvalues, lambda equal to 5 and lambda -1. This gave us eigenvectors 1, 1, and -1/2, 1. Anyway, that's pretty much it for eigenvectors, eigenvalues. They show up a lot in lots of different fields. Anyway, thanks for watching.